Hello everyone, this is Jeff Wilkerson, Professor of Physics at Luther College. This is our introduction to the Measuring Atomic Spectra lab. So what we have set up here for you is we have an hydrogen tube with hydrogen gas in it. We've got this Ocean Optics red tide spectrometer, and it's plugged in to the computer here. And we've opened up Logger Pro, so we have Logger Pro open on the machine here. And the first thing I'm going to do is I'm going to go up under Experiment, and I'm going to set up the sensor. And the sensor, you see, it's identified as Spectrometer 1 on there. I'm going to click on the Spectrometer 1. It says Absorbance. I'm going to turn that into Intensity. I want to measure intensity of the spectrum. Okay, you see that it changed the look of it right there. The next thing I'm going to do is the fiber, optical fiber that's collecting the data, that's pushing it to the spectrometer here. Not really pushing, but letting it flow to the spectrometer there. It's capped, so I'm going to take the cap off. I'm going to start collecting the data. And you see there's not a lot of intensity there. There's not a lot going on. And so you can start to see the lines appear right there as I get it pretty close. So the first thing we ask you to do in this lab, first thing I ask you to do in this experiment, as we're working in the lab here today, is to calculate the wavelengths of the lines that you would expect for the optical visible light transitions in hydrogen. And so you can start to see these lines appear right there. And so I can make them more intense or less intense by getting the thing closer or further away. I can scale the graph so I can see these things a little bit better if I wanted to. Should get this pretty close right there. There we go. So now you start to see a lot of these lines down in there that we can see. Two major lines in the visible region, a couple up here in the infrared region, and maybe you can see that, maybe you can't, I don't know. But you've got this, you got these lines. So what I would look for is to make sure that we're not flat topping these lines, so that we're getting these things read out. We can move these a little bit closer if we want to get better data in some of the fainter lines right here. But then I'm going to just stop this acquisition. Okay, and we're going to extract the data like we did before. So first thing you do, you come in, you're working the experiment, you do the derivation of where you would expect those lines to be. And we're going to start right where Bohr did when he made his model of the hydrogen atom. And so you're going to start by quantizing angular momentum, writing down the expression for what you know the force, the electrical force is on would be on an electron if it were orbiting the proton at the center of the nucleus, and then you're going to know what the kinetic energy and the potential energy are. We're just going to work through it. We're going to need an expression for what the energy levels are as a function of n. N equals 1. 1h over 2 pi is the first angular momentum level, 2h over 2 pi, 3h over 2 pi, 4h over 2 pi. We have all of those levels. The visible light lines that we're looking at here, we could work with the infrared lines there. We've got a couple of really nice infrared lines that would end in n equals, that would start, in n equals, would end in n equals 3. The visible lines would end in n equals 2. So we're making transitions 3 to 2, 4 to 2, 5 to 2, 6 to 2. Which of these transitions can we see down in there? And you see bumps across there. So you see various things in this spectrum. Once we have the spectrum taken, we're going to extract the data. So we're going to come up here, and you did this before, right? You did this with the RC timing circuit. And you're going to just say, I'm going to export this data, and you can export it as CSV, or you can export it as text. And so you have different ways you can export it. If you export it as text, you can cut and paste it into our kaleidograph. If you export it as CSV, you might be able to import it directly into kaleidograph. But what you want to do is once you have that file on the desktop here, or wherever it is you're storing it with your data, you want to cut it. So you only want to plot this a region around one line, and then around another line, and then around another line. So you want to plot each line individually. And if you've got enough data, if the line is wide enough, you want to fit a Gaussian to that line and use the mean of that Gaussian fit as the wavelength of that line. And then the uncertainty is going to be the standard deviation divided by the number of points used in that fit. And so you have to think about what that is. You have to think about what your uncertainty actually looks like in that case. And so you'll work with that just a little bit, and then we'll say, okay, this is good. Let's see how close we were to what we expected. So we're thinking about the width of this line right here is giving us something along the lines of precision that we've been talking about all semester long. Accuracy is how close the mean of this line is to where we would expect it to be. So we can think about the things that affect both of those. What affects the precision in this experiment? What affects the accuracy? If you're able to measure 4 lines or 5 lines, and maybe, looking at the data that's here in front of me, we did this work, I did the write-up to the experiment guide, to suggest to you that maybe you wanted to look at the 4 visible lines, but there's a couple of really beautiful infrared lines right there. So maybe we actually want to look at some of the infrared lines too, that are between 700 and 800 nanometers right there. So maybe those are the ones we want to look at as well. But in any event, think about how you want to think about what could be limiting the accuracy of this data. That is to say, are all of these wavelengths shifted by the same amount in the same direction from what you expected to get? If so, what caused that? Or what's going on? Are they shifted in the same direction but by a varying amount each time that depends on the wavelength of the line? What causes that? So these are the kinds of things I want you to think through as you're doing this. So this is what we're going to do here, is we're going to look at some of these transitions and see if we can fit them there and understand what the wavelengths are and if they're what we expected them to be. And so great, all of that is very good. And so now we want to move on then. After you've done that work, so you're going to spend a fair amount of time doing your derivation. You saw that data acquisition was really quick. You just saw me get all the data you need for the hydrogen tube. Then do the same thing for once ionized helium. You take one electron out, and what would you expect some wavelengths of in this same visible and maybe infrared region of once ionized helium? Predict some lines. Just try some transitions and see where they are. And if the line's too ultraviolet, if the wavelength is too short, then try a different transition that would give you a longer wavelength and see if you can predict where several lines in helium would be, and then go look for them. We're going to replace this tube with a helium tube and see if you can find those lines in the helium tube. And that's what we got for you this week. It should be fun looking at some atomic spectra and sort of analyzing what we see from the atomic spectra. And have a good week, everyone.